Welcome back. So, in our next video, we are going to cover polarity of molecules. You might heard the terms polar bond, non-polar bond. So that's what we are going to deal with today. So, but first we have to uncover some terms. Okay. So, for example, what does it mean for something to be polar, and what does it mean for something to be non-polar? So before we proceed with the actual terms, I want you to think of a magnet. So a magnet is a dipole. What's a dipole? It basically just means you have the positive north pole and the south pole that's negative, right? Okay, so it's a dipole. You have a positive end and a negative end. So molecules can be dipoles as well. Okay, they can be just like magnets. How? Because remember that the bond is just made of electrons. Okay. So let's say we have hydrogen and then fluorine. Okay. So this bond is an electron. Okay. These are electrons actually. And the thing here is if the atom is connected to a more electronegative atom, that means that the pull of electron cloud will be uneven. Okay. So let's take, for instance, the hydrogen gas molecule. So these are the same hydrogen gas. So they have an electronegativity of 2.1 each. Okay, so how do I know that? Just look here at the periodic table. It's 2.2 pala, sorry. So they both have a 2.2 electronegativity. Okay, so that means they have an equal tendency of pulling electrons. 2.2 sila parehas. So that means if you have an electron, they are just equally tugged into the opposite ends. So if there's a balance force, magiging spherical lang siya. Okay, so because everything's equal in all directions. On the other hand, let's have hydrofluoric acid, HF. So remember the electronegativity of hydrogen is 2.2. I don't know what's true with fluorine, so it's 3.98. By the way, the scale that we are using here is called the Pauling scale. He's the chemist or physicist, somewhere there. Because did you know that chemistry and physics are actually overlapping at most cases? Anyway, so the Pauling scale is showing us the measure of electronegativity. The bigger the number, that means the more electronegative an atom is. Anyway, going back to our example here. So if we look at the HF here, we have a higher electronegativity around the fluorine atom compared with the electronegativity of the hydrogen atom. So that means the fluorine is more electronegative. But what does it mean for an atom to be electronegative? So when you say an atom is electronegative, it will pull the electrons towards it. Okay. It will pull the electrons towards it. So that means instead of having the electrons look like this, para siyang foot long. So instead of having that, the electrons will be moved towards the fluorine side. Okay. So why is that? Because the fluorine is more electronegative. It will hoard more electrons to itself. So as you can see, there is an imbalance with the electron distribution. One side has more electrons than the other. But remember that the electrons are negatively charged. That means in this molecule, one side is more negative than the other. Do you see the correlation with the magnet? So a magnet is a dipole. One side is more negative than the other. because of course the other side is positive. But anyway, so that's the idea. One side is more negative than the other. So that means this is imbalanced in terms of electron distribution. Therefore, we can say that it's a polar covalent bond. So the bond is polar because we have this thing called the dipole. Now, if one side is more electronegative than the other, we usually symbolize it with this Greek letter delta, small letter delta, because you're probably familiar with the big one, the triangle. The small letter delta looks like an 8, but is incomplete. So since fluorine is more electronegative than hydrogen, and we know that this is a polar covalent bond, so we signify the side of the molecule that has more electrons around it to be partial negative, and the other side will be partial positive. So why do we coin the term partial? Because it's still a bond, no? It's still a bond. So the electrons are still moving from fluorine to hydrogen and vice versa, from hydrogen to fluorine. It's partial because they are not ions to begin with. They are not ions. Okay. If this bond is to be cut, that means you have an ionic bond. Okay. So that's the time when you can say that it's positive and negative. But if they are in a molecule, okay, and the difference is just the electron cloud is not balanced, so we signify it with the Greek letter delta, which means partial positive, partial negative. We assign the partial negative to the more electronegative atom, and then the partial positive to the side of the molecule that is less electronegative. Okay, so what are we going to do with the numbers here? Okay, well, depending on the difference, okay, so to be specific, the electronegativity difference, you can actually measure whether the bond is polar or not polar. Okay, for instance, let's look here. So this is the typical connotation that we have for a bond. Let's say you subtract the two electronegativities, and then you ended up with a difference between 0 to 0.4. Sorry. Okay. So let's say you end up with 0 to 0.4 difference. That means you have a non-polar covalent bond. So if you have a non-polar covalent bond, that means everything is distributed symmetrically throughout the molecule. That means there is no dipole here. Okay, so there's no dipole here. On the other hand, if the electronegativity goes beyond 0.4, say it becomes 1.8, that's the time you have a dipole. The dipole starts to appear. Okay, dipole is here. Anyway, so between 0.4 to 1.8, so you can say that that's polar now. So if you have a polar, this is the time you signify a partial negative end and a partial positive end between the bonds. But the electronegativity difference of 1.8 and above means that there is a very big discrepancy between the electronegativities of two atoms. So that means instead of just pulling the electrons from one side of the bond to the other, it will actually get the electron. And this is common if you have a metal and a non-metal, such as in ionic bonding. So any difference between 1.8 and above, you have an ionic bonding. So instead of having partial positive, partial negative, you just have a fully charged positive and a fully negative ion. This is the time when they become ions. Again, this is common for metals and non-metals. But for non-metals that we've been talking, so it's either the polar covalent and the non-polar covalent. So just remember the difference: 0, 0.4, 1.8. 0 to 0.4, you have a nonpolar covalent bond. Anything beyond 0.4 to 1.8 is a polar covalent bond, and then anything beyond 1.8 is a ionic bond. So take for instance, if let's say we have carbon, hydrogen connected to each other. So if we look at the periodic table, their electronegativity differences are here. So it's 2.5 minus 2.1. You have 0.4 difference. So it's here. So it's nonpolar. For carbon and oxygen bond, so electronegativity of oxygen is 3.5, carbon is 2.5, so it's always bigger number minus smaller number. So we have a difference of 1, which means it's polar covalent bond. So since oxygen is more electronegative than carbon, so oxygen will be partial negative, carbon will be partial positive. For NaCl, well, look at the electronegativity difference. It's so big. So yeah, it's ionic bond. So let's apply this thing with our previous examples. So let's take, for example, the molecule that we created last time, the CO2. So here in CO2, let's just focus on this carbon-oxygen bond. Okay. So for the carbon-oxygen bond, let's look up at their electronegativity. So let's use the periodic table again. So the electronegativity of carbon is 2.55, okay, and oxygen is 344. So this is 2.55, this is 3.44. Tama ba? Let me just check it again. Okay, so yeah, it's correct. So if we take the electronegativity of oxygen and carbon, so delta En, so that means you just subtract the two numbers. So again, it's always the bigger number minus the smaller number. So what's that? I think that's, I'm gonna use my calculator. I'm bad at this. Okay, so 0.89. So the difference is 0.89. Okay. So 0.89, if we look at the electronegativity difference here, so 0.89 falls under the polar covalent bond. So that means the bond there is polar. Okay, so it's polar. So I will ask you, which side do you think is the partial negative end? So of course, it will be the oxygen. And the partial positive end will be the carbon. So the bond is polar for the case of CO. Well, the same thing is true for the other side. Okay, so it's just still carbon and oxygen anyway. So let's move on. How about chlorine and fluorine? So if you look at our periodic table once again, fluorine is 3.98. This is 3.16. So it's 3.98 and then 3.16. So if you take the difference, what's that? I'm going to use my calculator once again, of course. Maybe I can do it mentally. So I think that's 0.82, if I'm not mistaken. Yeah, 0.82. So it's still polar. It's between 0.4 to it's higher than 0.4 but less than 1.8. So yeah, it's polar. So that means which side is more electronegative? But sorry, I mislabeled the electronegativities here. So that means which side is more electronegative? Of course, it will be fluorine, and then carbon will be partial positive. Okay, so that's it for the polarity.